There are two types of errors that are possible in any formal statistical decision, so we give them the nice descriptive names type 1 and type 2. A type 1 error is when we reject the null hypothesis because we find evidence against it, even though in reality the null hypothesis is true. A type 2 error is where we do not reject the null hypothesis because we don't find evidence against it, when in fact the null hypothesis is false. So we can easily distinguish which type of error we have based simply on whether we reject or we fail to reject. We've been using the language fail to reject instead of do not reject fairly commonly. So if we take a look at our tip and bill examples from section 4.3, we can identify what types of errors are possible there. First, we had our tip percent versus bill amount. Then we had our tip amount versus bill amount. So recall that in tip percent versus bill amount, we did not find evidence of a linear association between the amount of the bill and the percent of the tip. That maybe if the bill is larger, the tip percent might be larger sometimes, it might be smaller sometimes. We did not find statistically significant evidence of an association. So in this case, our formal statistical decision was fail to reject. H naught. If we fail to reject H naught, the only type of error that is possible is type 2, just looking up at the table above. In context, to think about what this means, we have to state both parts. So one part of that is that the null hypothesis is false or the alternative hypothesis is true. The other part of that is that we failed to reject the null hypothesis. Both of these pieces have to be present for this to be an explanation of an error. So if we just put a little summary, this isn't my answer, of course, because it's not in context. I have to say what it means in context to fail to reject the null hypothesis, and then I have to say even though the null hypothesis is in fact false, and I have to say that also in context. So I have written in the first half of this an explanation of what it means for me to fail to reject the null hypothesis. We did not find evidence of a linear association between the tip percent and the bill amount. And now we need to say the second part of it, which is even though the null hypothesis is false, meaning even though there is a linear association between tip percent and bill amount. So even though there is a linear association, or there is a linear association again between tip percent and bill amount, I think it's reasonable to assume that that is implied, that that's what we're talking about at this stage. But don't ever leave out one part or the other of this explanation, or else it's not an explanation of an error. Never assume that something is implied if we only say half of this. Okay, so that's the error. The type 2 error in this case is don't find evidence of a linear association, even though there in fact is one. And on our other test, the other test was tip amount versus bill amount. Just as a reminder here, by the way, our hypotheses for these were both the null hypothesis was that the correlation was 0, and the alternative hypothesis was that the correlation was non-zero. So the first one, the null hypothesis, is no linear association. If we have a correlation of 0, there's no linear association. The second, the alternative hypothesis, is some linear association. That's really why we're using the wording that we're using here. All right, if we look back to our notes from 4.3 at the tip amount versus bill amount, right? If we think again, like if everybody were to tip 20%, we would have a perfectly linear positive correlation. In reality, some people tip more, some people tip less, and that's where the scatter plot starts to look not like a perfect straight line. But in this case, we did see a strong linear association, as we would expect. So we did reject the null hypothesis in this case. And therefore, type 1 is the only type of error that is possible in this case. So what an error of this type would mean in context, now we want to explain reject even though the null hypothesis is true. And again, we have to explain both parts of this. I need to explain in context what it means to reject the null hypothesis here. And I also have to explain what it means for the null hypothesis to be true. All of this in the context of correlation or linear association, tip amount, and bill amount. Okay, so again, the first half, everything up to the comma, is explaining what rejecting the null hypothesis means in context. Everything after the comma is the even though, and then explaining what it means for the null hypothesis to be true. All of this must be in context. So our answers should never include the words that we see here other than maybe the even though, right? You should never include these fail to reject or H not true or H not false or any of that in our explanations in context. Another way to think about what the significance level alpha means is it is the probability of making a type 1 error. So that value alpha that we use as a cutoff for where we say if the p-value comes out to be less than alpha, now that we've established the language of type 1 and type 2 errors, what we're saying is that that's the probability of making a type 1 error using this rule, where the rule is determined by alpha. So generally, to follow this model here, we might say an alpha percent, right? We might convert alpha to a percent. There is a 5% chance of making a type 1 error using this value of alpha. So for example, if we were to repeat this study of tip and bill amount, say tip amount and bill amount, 50 times using independent samples, each with alpha equals 0.05, what is the probability of a type 1 error in each study? Well, that is just alpha. That's exactly what we're saying that alpha means. So alpha equals 0.05, or we might talk about that as meaning 5% chance. So let's just go with 5%. Now, how many type 1 errors would this amount to on average if we repeated the study 50 times? Well, that would be 50 studies, each with a 5% chance of making a type 1 error. So if I multiply that together, I get 2.5. So we would expect to see 2.5, meaning that we would expect to see 2 or 3 type 1 errors. Using this rule on a study of this nature. Thinking about alpha as the probability of a type 1 error helps us to understand what the importance is in determining whether alpha should be small or large. How acceptable is it to make a type 1 error? So that's what we're going to look at is several examples in context.